Now that you understand Dalton's law of partial pressures in gases and mixtures, we need to look at an absolutely essential component of gas, volume, and pressure in the body, and that's the alveolar content of gas, represented by the alveolar gas equation. This is fundamental to the understanding of hypoxemia in clinical practice. Fundamentals of Anesthesiology and Critical Care. With me, your host, Pat Nelligan. Understanding gases and vapors. This tutorial is on alveolar gas and the alveolar gas equation. We'll start with a clinical scenario. You're in the ICU and you're looking after Mark. He's a 39-year-old male admitted with hypoxic respiratory failure. His chest x-ray reveals extensive bilateral pneumonia, Haemophilus influenza. He has no medical history and he's been given 60% oxygen, that's an FiO2 of 0.6, to target a saturation of 92% on pulse oximetry. Blood gas is drawn, and on the blood gas, the PaO2 is 8 kilopascals or 60 millimeters of mercury, and the PaCO2 is 5.3 kilopascals or 60 millimeters of mercury. In order to quantify this patient's degree of hypoxemia, we want to know the gradient between the alveolar and arterial oxygen tension. Let's have a quick look at what we know and what we need to calculate here. We know that the patient is being delivered 60% oxygen, which is approximately 60 kilopascals or 450 millimeters of mercury. That oxygen passes through the lungs that are diseased, and there is significant ventilation perfusion mismatch and shunt. Consequently, the arterial oxygen tension is only 8 kilopascals or 60 millimeters of mercury. Clearly, this is a significant ramp between the inspired and the arterial oxygen tension. To quantify the degree of hypoxemia, conventionally, we calculate out the alveolar P big AO2 minus the arterial P small aO2 gradient. In order to calculate this, we need to know the alveolar oxygen tension. So let's work the problem. The first thing we need to know is the partial pressure of inspired oxygen. That's the PiO2, and that depends on the atmospheric pressure. At sea level, atmospheric pressure is 760 millimeters of mercury or 101 kilopascals. The percentage oxygen in the air is 21%. So the PiO2 is 760 multiplied by 0.21 or 101 multiplied by 0.21. And that works out at 160 millimeters of mercury or 21 kilopascals. Secondly, the air that we breathe is dry. By the time it arrives in the alveoli, it is fully saturated with water vapor, and water vapor is a gas. The saturated vapor pressure of water at 37 degrees is 47 millimeters of mercury or 6.3 kilopascals. This immediately reduces the partial pressure of other inspired gases by the same amount. This is Dalton's law. So the total pressure of gases is 760 minus 47 or 713 millimeters of mercury or 94.7 kilopascals. Third, there is always another gas in the alveolus, and that gas is carbon dioxide. Carbon dioxide is produced relentlessly during the day. The normal partial pressure of carbon dioxide in arterial blood is 40 millimeters of mercury or 5.3 kilopascals, and it's controlled by alveolar ventilation that increases if more CO2 is generated. Importantly, that CO2 is kept more or less locked at that level, and the CO2 in arterial blood mirrors the CO2 in alveolar gas. There is a relationship between the amount of oxygen consumed versus the amount of CO2 produced. So how do we calculate the alveolar oxygen content? As the water vapor pressure never changes, and the barometric pressure never changes assuming that you are at sea level, you subtract the expected alveolar partial pressure of CO2 from the PiO2 to find the partial pressure of oxygen in alveolar gas. So the PiO2 is 713 times the FiO2, in this situation 713 multiplied by 0.6. That works out at 428 millimeters of mercury, or 57 kilopascals. So the PiO2 minus the P-alveolar CO2 is 428 minus 40, and that equals 388 millimeters of mercury, or 52 kilopascals. However, the alveolar oxygen pressure changes dynamically due to consumption, and the partial pressures must always equal 100. As a consequence, to truly calculate out the partial pressure of CO2 in alveolar gas, you must account for metabolism. On a pure carbohydrate diet, oxygen is leaving the alveolus at the same rate as carbon dioxide is entering the alveolus. The alveolus stays the same size. But normally, more oxygen is consumed than CO2 is eliminated. The alveolus becomes smaller, and the relative ratio of carbon dioxide to oxygen is higher. As a consequence of this, a concept known as the respiratory quotient was developed. And for most of us, our basal metabolic activity consumes approximately 250 mils of oxygen per minute and produces 200 mils of carbon dioxide. The relative ratio of these two is known as the respiratory quotient. Why don't you calculate out the respiratory quotient for these numbers? In this case, we'll divide the total amount of carbon dioxide per minute by the total amount of oxygen. The answer is 200 divided by 250, and that is 0.8. The respiratory quotient depends on diet. For an exclusive carbohydrate diet, the respiratory quotient is 1. For a protein-exclusive diet, the respiratory quotient is 0.8. For a fat-exclusive diet, it is 0.7. And this is illustrated by the volume of oxygen produced per gram of substrate versus CO2 production. For carbs, they are equal. About 0.8 liters of oxygen and 0.8 liters of carbon dioxide are used and generated per gram of substrate. For protein and fat, there is significantly less CO2 produced per gram versus oxygen consumed. If you divide the CO2 produced by the O2 consumed, the result is the respiratory quotient of 0.8. In this example, this is for protein, but in a balanced diet, on average, the respiratory quotient is 0.8. Let's look at the impact on P-alveolar CO2 with different respiratory quotients. This patient has a PaCO2 of 40 millimeters of mercury, or 5.3 kilopascals. If the respiratory quotient is 1, the alveolar CO2 is 40 millimeters of mercury, or 5.3. If the respiratory quotient is 0.8, then the alveolar CO2 is 50 millimeters of mercury, or 6.6 kilopascals, because more oxygen is being consumed versus CO2 produced. The alveolus shrinking, and Dalton's law must be obeyed. If the respiratory quotient is 0.7, then the alveolar PaCO2 is 57 millimeters of mercury, or 7.6 kilopascals. Putting all of this together, we have the alveolar gas equation. The alveolar oxygen partial pressure is the atmospheric pressure minus the water vapor pressure multiplied by the FiO2 minus the arterial partial pressure of CO2 divided by the respiratory quotient. And for most of us, most of the time, the respiratory quotient is 0.8. To quantify hypoxemia, we need to use the alveolar to arterial PO2 gradient, the A minus AO2 gradient. In order to understand abnormal AAO2 gradient, you need to know what's normal. So let's look at that. The normal PaO2 arterial oxygen tension is 90 millimeters of mercury or 12 kilopascals. The normal partial pressure of CO2 in arterial blood is 40 millimeters of mercury or 5.3 kilopascals, and the normal FiO2 is 21%, 0.21. And we can feed this into our alveolar gas equation, knowing already what the water vapor pressure is. And this works out as follows. 713, which is the atmospheric pressure minus the water vapor pressure in millimeters of mercury or 95 kilopascals, multiplied by 0.21 minus 40 millimeters of mercury or 5.3 kilopascals divided by 0.8, the standard respiratory quotient. And the result is 150, 20 kilopascals minus 50, 6.6 kilopascals, and that gives us an alveolar oxygen tension of 100 millimeters of mercury or 13.3 kilopascals. To get the A minus AO2 gradient, we now need to subtract the arterial oxygen tension, and that's 90 millimeters of mercury or 12 kilopascals, and the difference is 10 millimeters of mercury or 1.3 kilopascals. That is the normal alveolar to arterial oxygen tension gradient. Let's go and have a look at Mark. Remember, 39 years old in the ICU with pneumonia. His FiO2 is 0.6. His partial pressure of oxygen in blood is 60 millimeters of mercury, 8 kilopascals. His partial pressure of CO2 is 40 millimeters of mercury, or 5.3 kilopascals. We can now quantify the degree of hypoxemia by calculating out the AA gradient. And let's work the problem. We have the same 713 or 95 kilopascals starting point, but now we're going to multiply it by 0.6, the FiO2, minus the PaCO2, that's 40, divided by 0.8. And this gives us a number of 428, 57 kilopascals, minus 50, 6.6 kilopascals. Our alveolar oxygen tension is 378, or 50 kilopascals, and from that we're going to subtract the arterial oxygen tension, 60 millimeters of mercury or 8 kilopascals, and the A minus AO2 gradient, you can work it out yourself, is 318 millimeters of mercury or 42 kilopascals. That is an enormous gradient. Now, the alveolar gas equation is an ideal gas equation and it has many, many limitations. Principally, it's not great at extremes of physiology. And our patients who are acutely critically ill in particular are at extremes metabolically, physiologically, and in terms of how oxygen and CO2 are consumed and produced. Clearly, you need to adjust the equation for altitude and consider in patients who are involved in, for example, house fires, that in carbon monoxide poisoning, the alveolar gas equation is of no value because most of the oxygen content of blood is attached to hemoglobin. We assume for most people that the PaO2 can estimate oxygen content by applying it to the oxyhemoglobin dissociation curve. But if hemoglobin is matted down with carbon dioxide, all bets are off. It also assumes complete equilibration between the alveolar CO2 and the arterial CO2, and that may not be the case with large increases in dead space and shunt, particularly if excessively high levels of PEEP have been applied. The respiratory quotient is an ideal number, but it's absolutely impossible to calculate accurately in acute critical illness because of autophagy, autocannibalism, and variability in how we feed our patients. And while I believe that the alveolar gas equation is a very important physiological concept that all anesthesiologists should be aware of, if you work in the ICU, you have probably never used it. If I was to go into our ICU and ask our bedside nurses what the patient's A minus AO2 gradient is, they would not know what I was talking about, but they would understand the concept because we use an alternative measurement. And that measurement, the PaO2 divided by the FiO2 ratio, that's the PF ratio, was introduced by the American European Consensus Conference on ARDS in 1994, more than 30 years ago, and it became the main way that we quantify hypoxemia in ICU. And this table was the core component of that particular conference. It's since been superseded by the Berlin definitions. So these days, to quantify hypoxemia in critical illness, we use the PaO2 divided by the FiO2 ratio. This can be calculated in millimeters of mercury or kilopascals. The PF ratio, PaO2, FiO2 ratio is such a simple way to quantify hypoxemia. The normal PaO2 is 90 millimeters of mercury or 12 kilopascals. The normal FiO2 is 0.21. So the normal PaO2 divided by FiO2, that's PF ratio, is 428 in millimeters of mercury, 57 in kilopascals. If it goes below that, it's diminished. It's evidence of developing hypoxemia. So what about Mark? Well, his PaO2 is 60. That's 8 kilopascals, and he's on 0.6 as his FiO2. So his PF ratio is 60 divided by 0.6, and that works out at 100, substantially lower than the 428 that's normal. There is a kilopascal calculation here, and that's 13.3. In my opinion, it's so much easier to work with millimeters of mercury than kilopascals for these calculations. So the normal PF ratio is a nice big roundy number. That's 400 millimeters of mercury or 53 kilopascals. As the ratio falls, the patient becomes progressively more hypoxemic. So moderate hypoxemia is a PF ratio of between 200 and 300 millimeters of mercury, 40 kilopascals. Moderate to severe hypoxemia, now this is not used in the definitions, but I think it's worthwhile, is a PF ratio of 100 to 200 or below 27 kilopascals. Severe hypoxemia, PF ratio of less than 100 millimeters of mercury, 13 kilopascals. And in the setting of pneumonia, that PF ratio of less than 200 is ARDS, and we call it severe ARDS if it's below 100. So the PF ratio is how all research studies these days on ARDS quantify hypoxemia. You need to be using it in your ICU on a daily basis as a way of making decisions about whether you should paralyze the patients, whether you should put them on controlled ventilation, whether you should turn them prone, whether you should consider using inhaled nitric oxide or putting the patient on ECMO. But just because the PF ratio is so handy, it doesn't eliminate the need on occasion to go back to the alveolar gas equation. And the reason why is the impact of hypercarbia. Imagine if Mark's PaCO2 increased to 60 millimeters of mercury or 8 kilopascals. His FiO2 is still the same, 0.6. What impact would this have on his P arterial O2? Let's recalculate the alveolar gas equation. So we have 713 by 0.6 minus 60 or 8 kilopascals divided by 0.08. And that is 428 minus now 75 or 10 kilopascals. And that equals 353 or 47 kilopascals. That's quite a significant amount lower than we saw previously. But if his lung injury is more or less the same, the A minus AO2 gradient is still 318 millimeters of mercury or 42 kilopascals. And in that situation, the P arterial O2 will be 35 millimeters of mercury or 4.6 kilopascals. Obviously, this is absolutely horrifying, and your reaction might be that we need to give 100% oxygen now, which under the circumstances would not be unreasonable. We need to get Mark's PaO2 up to the safe range. That's about 70 millimeters of mercury, 9.3 kilopascals. So how much oxygen do we need to give Mark to get his PaO2 up into the safe range? We know that the alveolar oxygen tension minus the arterial oxygen tension is the A minus AO2 gradient. That means that the alveolar oxygen is the arterial oxygen plus the AA gradient. we know these numbers, and our desired PaO2 is 9.3 kilopascals or 70 millimeters of mercury, and the AA gradient is 42 or 318 millimeters of mercury. Adding these, we can get the alveolar oxygen tension that will be required to bring the arterial oxygen up to 9.3 kilopascals or 70 millimeters of mercury. So let's solve this problem. We need to go back to the alveolar gas equation, and this has been solved to provide an alveolar oxygen tension of 52 kilopascals or 388 millimeters of mercury. What we don't know is the FiO2, but we do know the PaCO2 and the respiratory quotient, and that provides us with 75 millimeters of mercury, 10 kilopascals. That is to be subtracted from the alveolar oxygen tension. We can solve the CO2 component to 94 or 12.5. And now we can rearrange everything to put that CO2 on the other side of the equation. So we have 388 plus 94, and that equals 713. That's the atmospheric pressure minus the water vapor pressure multiplied by the FiO2. Rearranging again, we have 483, that's 388 plus 94, that's 483, divided by 713, and that will be the FiO2. You can calculate this out yourself, but the result is 0.68, 68%. That is not an awful lot higher than the FiO2 you were giving the patient originally was 60%. You did not need to go up to 100% oxygen. Nurses in ICU know this, that very small changes in the FiO2 can have big changes on the blood gas, but anesthesiologists in the operating room will frequently just go up to 100% oxygen and leave it there when they see a patient desaturating, and for good reasons. Let's review the tutorial. In this tutorial, we talked about the contents of alveolar gas, the impact of water vapor on alveolar gas, the impact of carbon dioxide and metabolism on alveolar gas, so that we could solve the alveolar gas equation. From this, we were able to calculate the A minus AO2 gradient. I subsequently went on to explain why the PF ratio, the PaO2 divided by the FiO2 ratio, has replaced the alveolar gas equation in most clinical practice these days because of its simplicity and the very nice round numbers that we have. But nevertheless, in situations, for example, where the partial pressure of CO2 in the blood goes up, the alveolar gas equation gives us really good information for helping us titrate oxygen therapy.